Okay, now we continue to learn Chapter 5, Orthogonality. Section 2, Orthogonal Subspaces. Part 2, Fundamental Subspaces. So here we will introduce fundamental subspaces, which are very important examples. Okay. We have this theorem 5.2.1, a fundamental subspaces theorem. If A is an n by n matrix, then the null space of A equals the orthogonal complement of the range of A transpose. So NA equals RA transpose is the orthogonal complement. And on the other hand, we also have null space of A transpose equals the range of A is the orthogonal complement. So we see the proof. It's not difficult to show that the null space of A and the range of A transpose, they are orthogonal. You can show that for any vector in null space of A and any vector in range of A transpose, the scalar product is 0. So they are orthogonal. So you know that the null space of A contains in the RA transpose is a orthogonal complement, because we know its orthogonal complement is the largest set that contains all the vectors that are orthogonal to RA transpose. So we have this inclusion. The null space of A is included in RA transpose orthogonal complement. On the other hand, we also know that for any X belongs to the range of A transpose is orthogonal complement, we know that X is orthogonal to the range of A transpose. And then from here, we can know that AX equals 0. So how can we have this conclusion? Because X is orthogonal to the range of A transpose. That means for any vector in range of A transpose, X and this vector, if you do the scalar product, is 0, right? And then you can choose one, for example, A transpose Z. So X transpose times A transpose Z equals 0 for any Z. For any Z belongs to Rm, right? And you can choose Z just equals A times X. Then this implies that AX transpose times this vector AX equals 0. So this means AX equals 0. So this means X also in the null space of A, right? Because the null space of A is just the solution set of the homogeneous linear system AX equals 0. Therefore, we have the null space of A equals the orthogonal complement of RA transpose. The same relation holds for the matrix B equals A transpose. If you write B here equals A transpose, then here is B transpose just equals A. So you have this part. And A transpose equals orthogonal complement of RA. So we show this fundamental subspaces theorem. So very important relations. Okay. Now we see example. Let A be this 2 by 2 matrix. The column space of A consists of all vectors of this form. Say alpha 2 alpha, so equals alpha times 1 2. So this consists all the vectors in the range of A, in the column space of A. Okay. And the null space of A transpose. The null space of A transpose consists of all vectors in this form, because if you consider the null space of this matrix, the first row should be 1, 2, second row 0, 0. So this means x1 plus 2 times x2 equals 0. So if x2 you set to be a free variable as beta, you will get x1 equals minus 2 beta. So this vector is in the null space of A transpose. And then it's not difficult to check that any vectors in Ra and Na transpose, if you do the scalar product, it's 0, right? Alpha times beta times 1 times minus 2, right? Then plus 2 times 1, so it's 0. So this show that for this example, we really have this fundamental subspaces theorem. Okay, holds. Okay, and now we have another theorem, 5.2.2. If S is a subspace of Rn, then we know that the dimension of S plus the dimension of S orthogonal complement equals n. Okay. Furthermore, if x1 till xr is a basis for S and xr plus 1 till xn is a basis for S orthogonal complement, then this set of vectors x1 till xr, xr plus 1 till xn, we combine those vectors together is a basis for Rn. So let's show this theorem. Okay, the first one, if S equals 0 only, if S is only this special subspace, and we immediately know that S orthogonal complement equals Rn, the whole space. Then of course the dimension of S plus dimension of S orthogonal complement equals 0 plus n equals n. And if in another case S does not equals 0 subspace only, this trivial subspace, then we suppose x1 till xr is a basis for S, and we let matrix X equals x1, x2 till xr transpose, which is a matrix of R by N matrix. And then we know that the rank of X equals R, because the rank of this matrix equals the rank of X transpose, okay, equals the dimension of the column space of X transpose. Because we are basis vectors, of course the rank is R, because it's a 4-column rank. Okay, and we also know that the range of X transpose just equals S, because if you consider X transpose, then you have these R column vectors, right? And these R column vectors form a basis for the column space of X transpose, and it is a range of X transpose, and it is also S because it contains all the linear combination of vectors of these basis vectors. So it is just S. And then by theorem 5.2.1, the fundamental subspaces theorem, we know that S orthogonal complement, okay, equals the orthogonal complement of Rx transpose, which equals the null space of X. Okay, so the dimension of S orthogonal complement just equals the dimension of null space of X equals this null space of X equals n minus R. Right? Because the rank is R, so the dimension of null space equals the number of free variables. So it equals n minus R. And to show that x1 till xr, xr plus 1 till xn, they form a basis for Rn, it suffices to show that those n vectors are linearly independent. Okay? Suppose that C1 x1 plus CR xr plus CR plus 1 xr plus 1 plus CL plus Cn xn equals 0. So this is linear combinations of given n vectors equals 0. And we see this part we can denote as one vector y. And this part we can denote as a vector z. And we know that y plus z equals 0. And this means y and z are both elements in S intersect with S orthogonal complement, because S is a subspace spanned by x1 till xr, right? So this means y in S, and because y, z here, z belongs to S orthogonal complement, because xr plus 1 till xn is a basis for the S orthogonal complement. And then here y equals minus z. by the properties of a subspace, we also know that minus z also belong to S orthogonal complement. So y belong to S intersect with S orthogonal complement. And similarly, you know that z also belong to S intersect with orthogonal complement. But we know that if a vector in both S and S orthogonal complements, this vector must be the zero vector. So we have y equals 0 and z equals 0. If y equals 0, because x1 till xr are linearly independent, so this means c1 equals till equals cr equals 0. And also, because z equals 0, this means cr plus 1 xr plus 1 plus till plus cn times xn equals 0. And because xr plus 1 till xn, they form a basis, right, for the S orthogonal complement. So they are linearly independent. So the coefficients cr plus 1 till cn cannot be other scalars, must be the zero scalars. So this means x1 till xr, xr plus 1 till xn, the whole set is linearly independent. So we know x1 till xn, they are really linearly independent and form a basis for the whole space. Now we give a definition for direct sum. If U and V are subspaces of a vector space W, and each W vector belong to this subspace W, can be written uniquely as a sum U plus V, where U belongs to the first subspace U and V belong to the second subspace V, then we see that W is a direct sum of U and we just write W equals U circle plus V. Then we have this theorem 5.2.3. If S is a subspace of Rn, then Rn equals S direct sum S orthogonal complement. So how to show this theorem? We use this way. The result is trivial if either S equals the zero vector only or S equals Rn. So this is a trivial case. Now we consider a general case where dimension of S equals R, small r, where R is greater than 0, smaller than n. Then for any x in Rn, we can write x equals C1 x1 plus till plus CR xr plus CR plus 1 xr plus 1 plus till plus CN xn. Okay, so to show the uniqueness, we first know that x1 till xr is a basis for S, and xr plus 1 till xn is a basis for S orthogonal complement. We denote U as a combination of x1 till xr, and V is a linear combination of xr plus 1 till xn. Then U belongs to S and V belong to S orthogonal complement, and x equals U plus V. In order to show the uniqueness, suppose that x can also be written as y plus z, where y belongs to S and z belong to S orthogonal complement. Then we will have U plus V equals x, okay, equals y plus z. And this means U minus y equals z minus v. And because U minus y belongs to S, z minus v belongs to S orthogonal complement. So this means U minus y belongs to S intersect with S orthogonal complement, and z minus v also belongs to S intersect with S orthogonal complement. Since the intersection of S and its complement, S orthogonal complement, just equals the zero vector, so we know that U equals y and v equals z. So the expression is unique. Okay. Now we consider this theorem 5.2.4. If S is a subspace of Rn, then S orthogonal complement equals S itself. So this one can be shown easily. You can just say on the textbook, page 280. Okay, and we have this corollary 5.2.5. If A is an n by n matrix and B belongs to Rm, then either there is a vector x belongs to Rn such that Ax equals B, or there is a vector y belongs to Rm such that A transpose y equals 0 and y transpose b does not equal to 0. So at a glance, you just see, oh, it seems complex result. But in fact, this corollary is very easy to illustrate. So why we see like this, okay? So given you any vector B belongs to Rm, given you any given matrix A, n by n matrix, so we have the range of A here, okay, like in this plane, graphically, and we have the null space of A transpose. Null space of A transpose, by the fundamental theorem, we know that it is orthogonal, right? Orthogonal complement of Ra. So it's like here, and A transpose here, and given you any vector B belong to Rm, B can only have two possible cases. One is in the range of A. Another case is B does not in the range of A, right? So if B in the range of A, of course, there exists vector x belong to Rn such that B can be written as a linear combination of the column vectors of A. So B equals A times x. So this is the first case, B in the range of A. The other case is that B does not in the range of A. If B does not in the range of A, then there is a vector y belongs to Rm such that A transpose y equals 0. So this means this vector y is in the null space of A transpose. Okay, so a y in the null space of A transpose and y transpose B does not equal to 0. This means B does not in range of A. If B in the range of A, of course, B transpose y equals 0. So this corollary just means that either B in the range of A or does not in the range of A. Okay. Now we see this example 4. Let A be a 3 by 3 matrix. Ask you to find the basis for the null space of A, the range of A transpose, the null space of A transpose, and the range of A. So it seems we need to do many works, right? To do the 4 bases, compute the 4 bases for those subspaces. We can do in this way. Given you this matrix A, we do the Gaussian elimination. We try to eliminate this matrix to be in the reduced row echelon form. Okay, and since from this reduced row echelon form, we know 1, 0, 1, 0, 1, 1 form a basis for the row space of A. It follows that this vector 1, 0, 1 as a column vector and 0, 1, 1 column vector form a basis for the range of A transpose. This means range of A transpose means the column space of A transpose. And this column space of A transpose is equivalent to the row space of A. Just you write the row vector in the column vector. You transpose the row vector to the column vector. So because these are the basis, form a basis for the row space of A. So this one just form a basis for Ra transpose. If X belongs to the null space of A, it follows from this reduced row echelon form of A that we have these equations, and then you can have x1 equals x2 equals minus x3. Setting the free variables x3 equals alpha, we can see that the null space of A consists of all vectors of this form, alpha times minus 1, minus 1, 1. Note that minus 1, 1 is orthogonal to 1, 0, 1 and 0, 1, 1. So this also coincides to our fundamental theorem, right? That is NA equals Ra transpose orthogonal complement. Okay. Now we continue, reduce A transpose. We do this transpose, and then reduce a row echelon form. Get its reduced here, and then 1, 0, 1, 0, 1, 2 form a basis for row space of A transpose. The row space of A transpose is in fact equivalent to the column space of A. So these two vectors, 1, 0, 1 transpose and 0, 1, 2 transpose, form a basis for RA, range of A. And if X belongs to the null space of A transpose, then X1 equals minus X3, because the first row tells you X1 plus X3 equals 0, so X1 equals minus X3. And the second row tells you that X2 equals minus 2 times X3. That's the null space of A transpose is the subspace of R3 spanned by, if you set X3 equals 1, so it's minus 1, minus 2, 1. And you note that minus 1, minus 2, 1 is orthogonal to 1, 0, 1, 0, 1, 2. So this also coincides to our theorem for the fundamental subspaces theorem that NA transpose equals orthogonal complement of RA. Note, a matrix A can be used to establish a one-to-one correspondence between RA transpose and RA. Indeed, every n by n matrix A is invertible when viewed as a linear transformation from RA transpose to RA. So given you arbitrary matrix A, if you consider this linear transformation, it may not invertible, right? It may happen that many vectors, if you do this linear transformation, you get many vectors have the same image, right? They have the same vector they get. However, if you consider the correspondence between only this RA transpose and RA, you can give the one-to-one correspondence, okay? Because Rn can be written as RA transpose and NA do the direct sum, right? And we also know that the dimension of RA equals the dimension of RA transpose equals the rank of A. See this example. Let's see this example. A is a 2 by 3 matrix, okay? And you can know that RA transpose is spanned by E1 and E2. So RA transpose, range of A transpose, which is a column space of A transpose, which is essentially equivalent to the row space of A. So it's just spanned by E1 and E2, right? And the null space of A is spanned by E3, because you need to have 2x1 equals 0, 3x2 equals 0, so x1 and x2 must be 0. Only x3 you can choose arbitrarily. So the null space of A is spanned by E3. Any vector x in R3 can be written as a sum of y plus z, where y in this form belong to RA transpose, and z belong to this form, belong to Rn in this form belong to RA, NA. And then you can write y equals x1, x2, 0, transform to A times y. A times y just equals 2x1, 3x2, okay? In this case, you will find the range of A equals R2, the whole space. And the inverse transformation from RA to RA transpose is defined in this way. If you only consider from RA to RA transpose, okay? So B equals B1, B2, and then you have the unique vector here. The first component is B1 over 2, the second component is B2 over 3, and the third component is 0. So in this case, from RA transpose to RA, they have the one-to-one correspondence. So in this case, in this sense, you can think it is invertible.